So, without any delay, we would like to start our next lecture 2 of this particular GAN program. Please, sir, please come on the stage.
Good afternoon to you all, and after a good presentation by yoga class, we are again coming back to our discussion. And so the second part is, the second lecture is on the tailings disposal method. And I will little bit touch site characterization. We cannot go much detail into it because later on in our discussion, day 4, day 5, we will go more detail into those kind of site characterization. But I will touch the site characterization. So, what is the starting point? Like like I mentioned, we start with a starter dam. So that starter dam is kind of a hydro dam. No mining materials are involved in that starter dam. So this is extra material. And this kind of design is started initially, like between 1960 to 1980. Majority of the structures based on this, which we will discuss next also, what it is called. But here, it is just I am showing how we are raising it. So we first built a starter dam, then comes the materials. These are all tailings materials. We normally call it a sand tailings or a slime tailings. You will see different. In civil engineering, you have sand, silt, and clay, all kind of particles. So based on that, so the sand tailings is mostly fine sands, where the slimes are mostly clay or silt kind of particles. So they are more fines, less strength, while the sands are little bit strength. So the sand tailing is the one where we are starting a new structure. So like that we go. And you can see that the slime tailings, there we will have the water. Also the surface water, we say that, we think that is under the slime tailings. So that's the distance from the crest to the slime tailing, that is called the beach. It's called a beach. It's normally a little bit sloped. We are here showing like it because it's standard concept, but it's a little bit slow because that slope allows the fines go further and further. And the width of the beach, especially in this kind of setting, the width of the beach is very important in the design of tailings dam. Now let us go to this kind of that I showed you. This is called upstream method. And how this is a very simple. You can see that it starts with a starter dam initially. Then we are putting this tailings in it, and those tailings, like we showed there, can be separated. But initially those separations was not there. So initially we call it like this, the deposited is like a whole tailings. Everything which was coming being deposited there, and you maintain that slope. And then the supernatant pond, that is called the any surface water or water from the tailings, because what happens when the slurry settles, the material will kind of settle down, water will stay on the top. So that creates the supernatant pond, and the distance between the pond and the crest is called the beach. So in this method, the beach width is important, because if there is no beach width, what is happening? The water is coming in contact with the dike very soon. Then we go to the next stage. So in the next stage, you can see that this, like the structure which we call is a dam, because this part is the dam, rest thing is the tailings. But that dam, normally we design it from the tailings and taking the sand part of it. So we took that sand part to build the next one. But again, the next one is going over the same tailings material. So for the second structure, what is the foundation? Foundation is the tailings. So initially in this structure, the concept was, the person who gave this concept, and this concept is very economic, because except starter dam you don't need anything, everything is there, and while you are building it, your space is still confined, you are not going to more space, rather than space is little reduced. But the problem is the foundation is the tailings. So the initial concept that after a certain time the slurry will settle. Once slurry settles, then it will generate some strength, because slurry doesn't have any strength. But it settles, it will generate some strength, and then the water will evaporate, and then when we start the next one, it will take some time. When we start the next structure, we think that it is already settled and strength, we can move the next structure. So that's how we can go on doing this. I have designed one tailings dam, which at the end will be 1200 feet height. And but the problem comes, like the people started doing this, that. Let us see the other ones and then I will see. Yeah, then once it complete, this will be the final structure we will get once it complete. So you can see that there will be some flow, but this part we are thinking it will be like a earth dam, because it will be drained. So in the drain one, it will drain and then there will be a flow seepage. What is the advantage of this upstream? This method is the lowest initial cost, because we are just doing a small starter dam in the beginning. Starter dam hardly more than 100 feet height. Starter dam, the beginning dam. That is the cost of the things. Because the rest of the thing is just storing, because we are again using the tailings for the construction of the dam, like sand part, and then the finer part going to the ponds. It is very good where the low seismic areas, and like I mentioned, 1960 to 1980 majority were all this tailing structure, and when 1980 they see some failures, then people went to the other method. So currently 50% in the world is the upstream design. Again, these tailings are mostly, like I said, we are bringing in, and from the crest we are putting all the slurry material there, and then the cyclone is used to separate fine and coarse. In the technology term they call it underflow and overflow. Underflow is the sand, overflow is the fines. But it was found that 60% of the dam which failed are the upstream. So most of the upstream dam is prone to failure. Even in some countries, I don't want to disclose the name of the countries, they have now banned, there won't be any upstream tailings. And the key failure is the static liquefaction here, because you see that one which was tailings and you go on loading it, in concept we thought that there will be no water, it is settled. But in reality that doesn't happen. That water is there, and if we load it, then it cause high and high pore pressure, and eventually it will fail. Then comes the next method. People thought that no, this upstream method, though it is less economy, but when it fails, like I mentioned, that 2015 failure, the court is giving fine like $30 billion. So if it fails, it's becoming very expensive. So to protect the failure, they came up with another method, which is called downstream. So here you can see that the starter dam, and the starter dam has an internal drain here. Because if there is, water will come, because the next part is the water. Water will come there. But if water will come, water will not stay there, because if water stays, when you go on loading, that causes the pore pressure. But you put a like filter drain, water can be easily drained out. So they the filter. But here you can see that when you go to the pore, number 4, how big is the actual starter dam here? It is almost 10 times higher than the actual starter dam. And here in the downstream method, we are not using any tailings material here. It is all what we use for the starter dam. So eventually it becomes a huge dam, and you can see that because that's kind of structure. And what are the main design? When like in the high earthquake, high seismic areas where people think that upstream dam is not viable, they selected this downstream dam. And again, the installation of drainage layer, and also in some cases they install also impervious core to protect the water into it. But the main disadvantage is the cost and the material. You need huge quantities of material outside the mines. You need that. And also it is highly expensive compared to the upstream dam. So though this is a stable structure but very expensive, again I said that economy also for the mining another important. So they have to again weigh economically viable or not, because if it is not economically viable, they will not go that and take the risk with upstream. But then comes another in between. This is called the center line method, which is currently becoming the norm, because the center line method, it is in between. It's slightly or partially going into the tailings and partially going into the outside. And one advantage is that this is raised vertically. The upstream one, you are raising it in the upstream direction. Downstream one, you are raising in a downstream direction. But in the central line, you are raising it vertically. And same thing here also, you need a filter, and all this, any water coming into it can be filtered out and can be seepage in the bottom. So you can see that this is the final method. And this is more stable, definitely more stable than upstream method. I have been involved with many upstream tailings dam. While raising, they change it. It was initially started as upstream, but while raising, they change it to the central line method. And again, the subsequent material, here the subsequent material can be tailings, also can be outside material you can use. And internal zones, like we have the filter, so it is here similar to things. And again, central line method also, if you compare to the downstream, requires a high volume of material, while the central line, the volume is reduced. And again, you can use both sand tailings, or you can bring in the higher drained material for the construction of the central line. Again, people also like did initially, this was more initially, they were using this structure also. This is like a dam, hydro dam. So you have like an impervious core, and then on the upstream and downstream side you have like a rock fill material, and then you have a filter zone or a riprap, and then you have the tailings. So this is kind of a, it's like a hydro dam or tailings, but this kind of dam will be only for a small scale structure. You cannot raise like you do like a 500 feet high or more structure like this. Tailings deposition, how tailings are deposited. Like again I said that mostly the slurry forms, they come through pipeline. And this is called a single point discharge. You can bring it and discharge it from the top. And this method is mostly employed that discharge slurry in the upstream of the pond. But this one is very common, the spigotting. It's like you have a pipe and there are several parallel pipelines which is connecting the main. So all the slurry coming through the main and being deposited along the crest. This is at a regular interval, this is done. But the future, what I was telling you, like right now this method is becoming the norm, because this is called the cyclone, hydrocyclone. The cyclonic method was introduced in around 1990s. So what it does, it differentiates fines and coarse. So that's why the coarse material go close to the crest, while the fines goes further to the pond. And we try to maintain a beach. Always we try to maintain a beach. Whether it is upstream, downstream or central line, the beach will be always helpful. Because if we allow the water come in contact with close to the dam side, then there is possibility that water will enter, and if there is filtration is there, but it all depends on how filter is working and if the filter is done correctly or not. Again, the deposition of filters, construction of filters, all should be again taken care of when we look into the actually what we design and in reality it is happening. So That's why it's underflow that is used to construct the tailing embankment, like the sand portion, while the overflow is discharged through a slime pipeline to the impoundment of the pond. Then comes the site characterization. This site characterization is a continuous process. Definitely when we start a tailing dam, like put a starter dam, we need to again make sure that our foundation is stable. But in further, whether we go centerline or upstream, then the tailings characteristics is very important. So in the raising process, we again go back to the tailings and collect the sample from there and then check that, like how strong is those tailings are. So in the site characterization, we look into the regular geotechnical field investigation like in the beginning. In the beginning it is the same as any dam you are constructing. You go to the site, look at the geology, look at the soil type, look at the rock type and do all kind of analysis. So you collect the coring or drilling and the sonic method. How many people are familiar with sonic method? Is it in India is available? You have sonic rig? No. What is the difference between sonic? Again, the coring everybody knows, because coring you do with the rock. Continuously you will core the rock in the subsurface. But in the auger sampling, like which we call SPT, we do that only in every 5 feet or 10 feet depending on what are the requirements. So in 5 feet or 10 feet you collect a sample through the SPT sample and get it. But sonic is a method where you can get the continuous sample. And like right now in most of the project I have worked, I always recommend to do a sonic rig, like to do the sampling using the sonic method, so that we can easily see those samples, what exactly they are subsurface, coming from the tailings.
So sir, sonic is a continuous sampling or continuous testing? Yes, it is continuous sampling.
It's a continuous sampling.
Continuous.
It will do the continuous.
Because in SPT we get the sample at 1.5 meter.
Exactly.
Here, like for 5 centimeter, 10 centimeter, 15 centimeter, continuously get.
It is continuously sampling, like coring.
Okay.
Coring does only in the rock,
Yeah.
hard rock.
Correct. So
But this sonic can do in any structure.
any soil, and it is a continuous.
It's a continuous
sample.
process.
Continuous
And it is very good for tailings, because tailings is not that hard or thing, so it is very suitable. Only thing is that it is a process of vibration.
Correct.
So we have to, we do not use it if is already the dam is classified as a very weak dam.
Right.
There we normally don't do that. Yeah.
So, and it is undisturbed, considered as an undisturbed sample only?
It is considered as a undisturbed sample, but the main thing is you may not get you have this
Shell
SPT.
by tube for
Exactly.
clay soil.
Exactly.
We use
So,
shell by tube for.
but you can stop it and take the sample if you want. Yeah.
So it's undisturbed.
Undisturbed you can do that. And then we do some test pits, but the test pits is initially for tailings test pits doesn't do much. But we have like geophysical testing. I will show you one slide there. And again the site reconnaissance generally, like you send geologists, they look into the site, and that is when the initial thing. And we do a lot of laboratory testings, and the main part for our seepage analysis we need hydraulic conductivity test, and for stability analysis we need the strength test. And in the strength mainly the shear strength of the material. Then hydrological evaluation, also in the site characterization is a part of the things. We go there, collect the climate data, collect whatever data available there, and also for the geotechnical evaluation we do seepage and stability analysis, and also we do geochemical evaluation. Then the environmental assessment. In the beginning of the site, the environmental assessment is the opening statement kind of when we do that, because for any site to get a permit it has to be environmentally safe. So environmental assessment is the first record, the first document produced, and that will lead to the other things. Normally when initially we started, we are following the same principle. Like we thought tailings is a soil. So in the soil we have experts and we go and do SPT test to find the N value. So anything we can design using that. But when people saw that in the tailings, it's not giving much information. Yes, the N values are low. But what these low N values are telling us? This dam cannot be used or it can be used. So that's where the cone penetration test came. Around 1980 it started, but in 2000 it has become more prevalent. But finally, right now, all the tailings site should have the CPT data. The CPT is the cone penetration test, which I will again go more details when we go into our case studies. I will show you how we collect the CPT data. But in general, we get a cone penetration, like a cone test strength, QC, and then there is one slip friction, and this is the slip friction ratio. So your cone strength and then the slip friction ratio, they kind of determine what is the material. Another important thing in the cone penetration test, which we cannot get that from any auger testing or SPT testing, is the dynamic pore pressure and also static pore pressure. You can get both. What we do in a dynamic pore pressure, we get the value. When we are doing it, we see that. Then the static pore pressure, you cannot do it continuously because it requires more time. Each test requires minimum 1 hour. So at certain intervals, we do the test. Normally, I tell the people to do at every 20 feet. But if I am there, I will look into this cone, dynamic cone data, and then decide, oh, here I need a test. Then they will stop there and do the test. That is the test data I am showing. This is the pore water pressure. And you see that it becomes stable. Once it becomes stable, that gives me at that particular point, that is the static pore pressure. And that's a very, very important parameter. I will show you how we use this parameter to come up with our strength data. And this is like again, at each point we get the stable value, like the steady state value, we call that is a steady state value. Those are the points we have plotted here. This is called CPTU, where we do the pore pressure testing. If you don't do the pore pressure testing, then you say it only CPT. Then the next is the SCPT, like it's a seismic CPT. What it does, the additional parameter it gives us, the seismic velocity also you can get. In the subsurface, you can get the seismic velocity both longitudinal and also shear. You can get both longitudinal wave like P wave and S wave data you can get also. But if you see the seismic data is also important, but the S waves, we know that S waves is not work if there is water, because S wave doesn't penetrate through the water. The P waves only penetrate through the water. But you can see that there is some forced water table, how we can determine from the P wave data also.
So, sir, P wave is, you said P wave is horizontal and S wave
P wave is the longitudinal.
longitudinal.
Oh, S wave is
Horizontal. S wave is the horizontal.
horizontal. Yes. So, but roughly, if there is no water, they are like we collect the, but shear wave data is actually very important for all analysis purpose. But in most of the cases, it's very difficult to get shear wave data. But from the P wave also we approximately calculate S wave because it's kind of half of the P wave, the value. But again, actual number can be different, but it helps us in like qualifying, like comparing whether it is high or low or for example. So again here also SPTU, you can also get the water pressure data at different depth. So this is the cone strength, which is normalized with the help of overburden or the effective stress, and then the ratio. This is a normalized because no unit. There is no unit in this plot. And this is also ratio, no unit. It's a percentage. So here, using this plot, this is developed by Robertson based on the CPT data. So in this plot, we can find like there can be 7 different soil type. It's called soil behavior type analysis, SBTN. And so you see that CD equal to 70, that CD is calculated using this formula. So above 70, if CD is above 70 or CD is below 70, that creates a completely different behavior. What is that behavior? It's called dilative versus contractive. What the contractive behavior? Because for simple example, any soil liquefied, the contractive soil is prone to liquefaction, not the dilative soil. So dilative soil more kind of a drained kind of condition, while the contractive soil is more kind of the undrained kind of conditions. So the drained and undrained strength, that we will discuss more on that when we look into the case studies. We'll see that how the drained behavior and undrained behavior is the key issue to decide whether the dam is stable or dam. Because initially when I was reviewing the data, before 2000, most of the analysis for the design was done using the drained strength, because that was the assumption. You put it there, but with time water will drain out, water will do that, it will become a drained material. It will not behave like a undrained. But in reality, it didn't happen. And when they found the failure, when I look into the failure analysis, everybody come up with that it fell due to the undrained shear strength. We will again little bit go more into this, how we do that. And here if you see the CC and CCS, these two soils are critical soils. If you have that kind of soils, then it can cause problem. Geophysical method. Again, these geophysical methods are used, but whether you can clearly take this interpretation and use it in the design that is not, there is no guideline for this. So it all depends on the experience. I am using geophysics for all 30 years. Like I am very fortunate, there was a geophysicist who was an engineer also. He was an engineer from MIT, but then when he joined the oil industry, there he became the geophysicist. And when he came and joined our consulting field, then he applied all his geophysics things into the civil engineering construction, and we became a good team. I worked with him for 25 years. So I was in most of my project and modeling, I always use geophysics. But again, in general, this is, I think these are the three methods which can be used in the characterization of tailing dam, that is called electrical resistivity. So you can see that you can find the dry tailings and you can see the saturated tailings, and also you can see the partially saturated tailings. That can do that, but again, it's not that you get it from this side means you will get it at every side. You have to be careful, cautious. So here I am using the word cautious. It's not the guideline like this is what will happen. But again, the electrical resistivity works very well if really you have a saturated zone there, like a phreatic water table. Most of the tailings I have worked in, because I worked in a very dry climate. In the dry climate, these tailings have water in it, but there is no like a phreatic surface developed there. There are like paused waters, like I call them is the pocket, water pockets there. But it's very difficult to find those water pockets using that electrical resistivity method. But then comes the seismic refraction, or REMI or MSW, like they say that, it's mostly the shortest wave. That also can give you some idea about the strength, what is the material there. This is example coming from a dam site where you can see that in that dam is a rock-filled dam, so there are also some boulders in it, so the seismic refraction can easily identify that. This is a new technique coming recently. They are calling it nuclear magnetic resonance method, where I have seen that in one or two projects. I have reviewed it, but again, still more knowledge is required. But what it does, nuclear magnetic resonance, you can see that you can easily identify the saturated tailings, like the pocket tailings. They say it can be easily identified. So it is still going on under research, and people are still working on it. Again, you know that any geophysical method requires a lot of interpretations. And again, you have to be familiar with the product, what you are doing, like the site, the tailings, what kind of behavior tailings has, where if you know that, then you can easily interpret this geophysical. That's all for today. And if we have some time for discussion, any questions?
Yes.
Sir, you have mentioned that cone penetration test is required for the tailing and design.
Yes.
But sir, in India, I have worked abroad also, sir. I know, like in Gulf country, Singapore and West Africa, that area people use cone penetration. But in India, you must be knowing that generally still cone penetration test is not that popular. Client generally goes with the SPD only because it increases the geotechnical investigation cost. So, like if we have only SPD data, can we design the tailing dam or not?
Again, it depends on what kind of SPD data you are getting there.
So that's
Can
the
you
Indian standard
able
code.
to identify, because in your tailings also you have water in it.
Yeah.
So do you see a big difference in SPT when there is water or there is no water? Can you
Yeah.
differentiate that? You can
No,
identify
no,
that.
That cannot be different. We cannot.
Then
differentiate.
how it will help you?
Yeah, sir.
The data. Yes, you can collect the data,
Yeah.
but how the data will help you?
Yeah, sir. So for our upcoming project, we have discussed with one of the international consultants. We told him that we have not done the investigation with CPT data. We have done only with the SPT. Will that suffice? Will that geological data will suffice to design the red mud dam? So they agreed upon that. They said I will design with SPT also.
Again, you
They are also international.
you can conservatively design it.
Yeah.
Like you think that this is a contractive material and design it. Conservatively, you
So
can
yeah,
do
because
that.
as you
but-
mentioned that with CPT it is more accurate and CPT data is required. Still we are like there are some consultants who are designing with SPT. So
Again, especially the important thing in the tailings is not the strength. The important or the key parameter is the pore pressure.
right.
But right now, that's what I will go in day 4 and day 5 and show them how this is the way we should do that. Because in the literature and also in the current field, still people do not have the solution for the pore pressure. But the pore pressure we are getting mostly if we install a piezometer.
Correct. Sir.
But
You are right.
where you will install piezometer?
Yeah, at initial stage we cannot.
You cannot
Initial
install
stage we cannot.
piezometer is a big structure.
Yeah.
So CPT data I use CPT data to install the piezometer. CPT data will guide me where I will put that piezometer.
Right.
Because CPT data gives me the pore pressure.
Yeah, CPTU you said you.
Exactly.
Yeah. Correct.
Without CPT, you have no idea of pore pressure. With SPT,
Yeah, with SPT
No.
we cannot measure the pore pressure.
exactly.
We
So,
cannot measure.
if you think the pore pressure is my key design parameter, definitely you need CPT. But again, the standard method, what people are doing from the very beginning there was no CPT.
There was no CPT, yeah sir.
Can-
Yeah, that research came later. CPT was.
If you see, if you go back to the general soil mechanics principle,
Yes sir.
in 1960s, 1940s, there was nothing,
Correct.
no data.
Yeah.
Still we have building big structures.
Yeah.
But the problem is, if you go and look at those structures and compare the structure we are building now, there is a big difference. You cannot build those structure now. They will be very expensive. But now with a lot of data, we are able to build good structure with less expense. Because we have the data, we know exactly what to do, so we are doing that.
Right sir. Okay sir. Yeah, that's it sir.
Sir, both the tests, we have to collect the sample from field and send it to the lab. From lab, we have to collect the data. No?
Again, the lab data is important. But this, if you have good CPT interpretation, we can get data from the CPT also.
Site.
Yes, from the site. Yes.
Okay. CPT is the on-site test.
Yeah.
We can get the result at site only during test.
Exactly.
Okay, so that is
But sir,
beneficial.
C and 5 parameters so we cannot get from CPT sir.
CPT, we can, again, the problem with the tailings is that's the main thing. Because you see the tailings, and I will show you when we go to the details, I will show you, because we are doing this sonic drilling. The person who was logging asked me how I will log it. I gave him one solution. Go to every 1 feet and tell me what you observe there, every 1 feet. In 1 feet, he found there is fines, there is intermediate, and there is coarse tailing. So, what kind of data You will get out of that.
Yeah, but sir, for designing, like for this analysis, we need the shear parameters of the CL5.
No,
that
again-
we can't get from CPQ, sir.
No, again, the C and Phi parameters for drain conditions, you can get that from laboratory.
Yeah. Even undrained also, sir.
Huh?
Undrained also we can get. from
Again,
the-
undrained you can get that, but again, undrained sample, getting the undrained sample is not that easy. To get the perfect sample, because I told you, in 1 feet sample, there is all mixed.
Yeah.
So how you can determine the fine strength from a mixed sample?
Yeah.
The sample you are doing should be coming from the only fine soil.
Yeah. For clay soil we can get, sir. at
Yeah,
least a
for the
sample
clay soil you can get.
And we
but
can do
that-
the undrained extraction technique.
Exactly. But the tailings is different. Tailings is clay only for the gradation. But it's not a clay-like material. Like it's a, your values are not that high.
Right, sir.
PI values are low here.
Plasticity index, yeah.
Exactly. Plasticity is low here.
Yeah. So
That's why it is more prone to the liquefaction.
more prone to liquefaction.
Yes.
Okay. Yeah. Okay. Right. So here, like for tailing, tailing comes into which classification, sir? This tailing material comes into which classification? So like NL, CL.
No, that's why I'm telling you. It belongs to everything. You see that. It's a clay-like, sand-like, silt-like. It contains everything. It's a mixed. That's why initially people thought that it is coming from the soil mechanics. There is also another differentiation. In the soil mechanics, you see the whole thing coming from a basin structure. In natural, it's a basin structure. So in the basin, if we go towards the depth, at depth, you see that the strength is increasing. That's what also your principle says. The strength is higher at depth. But that is not happening with tailings. In the tailings, even I have seen myself at depth of 500 feet, there is this slurry.
Right.
So I turned it, basin, tailings is a inverted basin. You are going opposite directions.
Right. Okay. So last question from my side. You mentioned about the pore water pressure, and in that you mentioned two categories, like static pore water pressure and dynamic pore water pressure. What is the difference, sir? I would like to know
No,
that.
the dynamic pore water pressure is like when you heat, because it's a cone. The cone is heating. So when it heats, immediately it creates a value. So this is kind of not telling us the proper pressure there. Because the water pressure, like what we assume, water pressure is based on the strength, like the load, upper load. So that's why the dynamic pore pressure is generally a little bit higher than the static.
Yeah, that is true, sir. But I'm saying, what is the difference? Like, what is the practically what is the difference?
Practical
Pore water
difference.
pressure is the upward water pressure,
Exactly.
right, sir?
But
Now, what is the static and what is the dynamic? I would
yeah,
like to
that's what I'm saying.
Yeah.
The dynamic is giving you a very high pore pressure. But that high pore pressure is generated due to the drilling process. It's not the actual pore pressure there. That's why we do that test to find the actual pore pressure. So that pore pressure, the static pore pressure we are doing, that is kind of considered similar to the, if you put a piezometer there and measure it, that value will be similar to the static pore water.
So dynamic pore water pressure can't be used in design.
It will be very difficult, but what it helps us, initially what it helps us to tell us that there is high pore pressure here. But what is
that depth?
exactly, but the number
Is
cannot
not
be
useful,
used.
cannot.
Number cannot be. You have to do a test to get the number.
Right. Understood, sir. Thank you, sir. Thank you.
If you want, I will qualify that static and dynamic. Just a simple example.
Yeah.
Suppose groundwater table is at suppose groundwater table is at 2 meters below the ground surface. Now 212 piezometers. Okay. So that gives what pressure.
Yeah.
Okay. Now you are building on a structure. Okay. Suppose today we are putting 10 kg. tomorrow 30 kg, 100 kg, 1000 kg. So that core water pressure will gradually increase.
Yeah.
That is the dynamic pressure.
That is the
So
dynamic pressure.
that we are getting from the CP2, because in CP2 bone is penetrating. That creating vibration. That we are simulating to this construction work.
Okay.
Because when you are filling up the tailings, that weight is increasing day by day.
Correct.
Clear? If the rate of this deposition is high, then that core water pressure development will be high.
Okay.
If there is no deposition, the water table will be at that deposition. That is the static condition.
Okay.
So this is the means if you correlate to the field and to the physics or mechanics. That is the
Correct.
now I go to
We will go into more details.
Yes, sir.
so sir will be explaining. So I think that will okay.
Yeah.
And this you again you are coming saying C and phi.
Yeah.
Okay. That generally used for stability analysis.
Correct. Slow stability analysis.
But that cannot give us the liquefaction condition. Liquefaction analysis is different.
Yeah.
So here C has no role. Clear? So that's why. So this C by when you are getting from the triaxial test, okay, that depends upon conditions.
Correct.
One is on drain, another is drain condition.
Correct.
Okay.
Correct.
Now major important is our on drain condition. Okay. In on drain condition, there is possibility that material can give C value 0, even if it's clay.
Is it?
Yes. Even if it's clay, we'll get cohesion is 0. That's why in most of the analysis generally that we are considering C value is 0 for the conservative point of view. Because you are assuming C value and finally there will be certain condition, same material that will show C equal to 0 in the underlying condition. So there is a term we are saying normal consolidated, Sarah will be saying consolidation part. So depends upon the degree of consolidation. So depending upon that, same material will behave as a sandy type material, same material will behave as a clay type material. So that is the tailings, that's why we cannot consider it is simply as a soil. Its behavior is completely different.
Right.
And it's practically difficult to judge.
But generally, when we do the normal foundation design for building or any plant or any structure, we go for untrained condition shear parameters only, because that we simulate that in the laboratory and in the field also it is existing.
That depends
Because
what is your type of structure, what is its utility, what is your position of water table below the ground surface.
Yeah.
Okay, if your water table is far below the ground surface, then we can consider this a drain condition parameters.
But like some of the books, foreign author books also, I have read that they said that water table can be increased at any time during rain season, monsoon.
Yeah.
So you have to consider water table if it is, let us say, 5 meters.
Then again
you have
we
to
have-
consider at ground level and design the foundation.
Then
That
again
is
you
what
have
they
to
are
see
suggesting.
what type of this grain size distribution. Whether it is a granular material or it is fine material.
Yeah.
If it is a granular material, then we assume there will be drainage of water within the when we are applying the load. But if these are fine particles, water cannot be drained out.
Cannot be. Clay
Then
type of
core
material,
water pressure will be developed.
Yeah.
Other condition we have to go for on drain condition.
undrained condition.
So it depends upon.
Yeah, generally for clay, I was talking about clay only.
Yes.
Clay material.
So
we have to
that's why
simulate with the
again
laboratory.
in clay, suppose that the location is already 10-story building. Suppose one example I am giving. Already 10-story building is there and it is demolished. Okay, and we don't have idea. It is already 20 years back. It was a 10-story building. Now this is completely demolished. Now we are going to construct one new building. Suppose it is we are planning for 2 or 3-story building. Now that soil is already consolidated. So there whatever will get C5 clear. So there is a possibility. So we may consider that C may be 0. That consolidated on drain condition there we may get C 0. There is possibility. That depends upon at that time what is our soil condition and how much loading we are planning to apply on that base of foundation.
Yeah, if previous building was demolished, then all the consolidation settlement has been occurred on
Yes.
in the soil. So
Suppose
there will
we
be no
don't have
further
idea.
consolidation.
Question is now suppose we don't have idea. Earlier 20 years back, whether there was a building or no, we don't have any idea. That's why we are going for this soil investigation.
Correct.
So from the soil investigation, we'll get all these idea.
Yeah.
It's a history of the soil.
Yeah.
already.
Yeah.
Clear? So that's why we cannot say that soil is a material or these tailings. Okay, these are unpredictable. Not like this is cement, steel. They have same behavior.
Correct.
Clear. But these have different behaviors depending upon climatic conditions. So many factors.
True, true. Again, coming back to your how you determine the C from the triaxial.
More circle we plot, sir.
No, you have 3 samples.
Yeah, 3 samples.
What is the assumption of those 3 samples? The 3 samples should be equal.
Yeah.
If one sample is different,
Ah.
you cannot make a point there.
Yeah.
So
Cannot.
getting the 3 equal sample from the tailings was very difficult for me when I worked in the when I started working. That's where, yes, the laboratory strength will give me some idea, but the CPT will give you the answer.
Correct.
I will show you
Yeah.
how CPT will give you the answer.
Okay, sir.
Because this undrained strength can be directly we can get from CPT.
From CPT.
Exactly.
Okay.
Okay, thank you very much. So for now we are running short of time. Let's have a quick tea and come back here in 10 minutes and we have our next lecture.